Sam and my batchmates Anto and Sneha, we did a project in LP, and this was our objective: maximize z is equal to 5x1 plus 4x2, and these were a set of constraints, and these were the constraints. We converted the inequalities into equalities and added the slack variables. These are technological coefficients. These are variables. These are right hand sides, and these are cost coefficients. And we take x3, x4, and x5 as the basic matrix, that is uh, and we take it as a basic matrix, and we take x1 and x2 as the non-basic variables, and we find xb. First step is to find xb. The formula for xp is this: b inverse b, and we get a value of 43 and 12. This should be greater than 0. And similarly, next we find the objective function value z is equal to cb into xp, and we get objective function value of 0. And next we test for optimality. Optimality is tested for the non-basic variables x1 and x2, and this is the formula for testing the optimality. And we get we get a value of -5 and -4 for x1 and x2. So for maximization problem, if the values are greater than 0, the solution is optimal. If it's less than 0, it's not optimal. In that case, you have to take the minimum negative value. So we take -5 as a variable which enters the basis. And next we find whether the problem is unbounded or not, and this is the formula for finding whether the problem is unbounded or not. And we get a value of 5, -3 and 3. For problem to be unbounded, all these three values should be less than or equal to 0, but we have two values greater than 0, so the problem is not unbounded. And next we go for the minimum ratio test, where where minimum ratio is xb divided by the entering basic variable a1. So xb is 43 and 12, and the minimum and the entering variable the matrix for the entering variable is 5, -3 and 3. So we divide this by this, and so we get a value of 8, -1 and 4. We should take the minimum positive value of these three. So 4 is the minimum positive value, that is x5. So x5 will be leaving the basis, and we shouldn't consider negative or zeros out here. In case of a tableau, the row 0 will give you the cost coefficients, and you have to take the right hand side of the objective function value is 0, because we move all the right hand side, the x1 and x2, to the left hand side. And the technological coefficients are given in the row 1, 2 and 3, and similarly the RHS. And we have to take the minimum first choose the minimum, like the least negative element for maximization. Choose the least negative element in the row 0, so that is -5. So circle that column. Similarly, find the minimum ratio, that is RHS divided by the column you just circled. So 40 divided by 5, that will give you 8. 3 divided by -3, that will give you -1. 12 divided by 3, that will give you 4. And find the minimum value in this minimum ratio test, and 4 is the minimum value. So just circle that circle that whole row. The intersection of the column and the row is the element to be pivoted, so this has to be pivoted to 1, and all the other elements in those columns should be made 0 by elementary row operations. And this is the graph for the first thing, where x1 and x2 are non-basic variables and are equal to 0. So this is the initial basic feasible solution. And next is similarly x1 enters the basis, and x5 leaves the basis, so x5 becomes a non-basic variable. Similarly you find xb, and similarly you find the optimality test. And if there's a negative value, that enters the basis. And similarly you find unboundedness, and you find one value greater than 0, so it's not unbounded. And next you find the minimum ratio test, that is this xb 25, 15 and 4 divided by the a2, because that's going to be the entering variable. So that will give you a value of 60 by 17, 15 by 0, and minus 12 by 1, that's minus 12. So these two are not considered because of 0 and minus 12. So the leaving variable should be x3, that is the first variable, x3, x3, x4 and x1. So x3 should leave because that has a minimum positive value, the only positive value in fact. And similarly the same way you have to do the tableau form. For example, find the minimum element in row 0, so minimum negative element, so x2 will be the minimum. Similarly, find the minimum ratio test, and you have to pivot this and make the other columns in that 0, make the other elements in that column 0 by elementary row operations. And in this case x1 has a value of 4, so this is the basic feasible solution for this, and x2 is still 0, so this is x2, so it stays here. This is after the first iteration. And similarly you do the same operation for the second iteration. So x2 enters the base and x3 leaves the bases, so you find xb, and similarly you test for optimality and you find the z value and then test for the optimality. Right here you have a 0, so even 0, it has to be either it has to be negative, or even 0 can enter a basis, so next we find the unboundedness condition, and we find two values greater than 0, so it's not unbounded. Similarly, find the minimum ratio test, xb divided by a5, so we get a minimum value for x4, that is 15. And similarly x4 will be the leaving variable, and x5 will be the entering variable, since that is equal to 0, the least possible number. So even in this row you can see that x4 and x5 are equal to 0. So right now x4 is in the basic basis, so we are replacing x4 by x5 because even that has 0 in row 0, that has a 0 value in row 0. So similarly so this has to be the entering variable, and we find the minimum ratio test, and we have to pivot this element. So we have to eliminate this element x4, replace this element by this x5, and this is a basic feasible solution. This is an optimal solution because it is we have both the values greater than 0, so it's an optimal solution. So, but we are just trying what's going to be because as even the cost coefficient for phi is 0, we find what's the value. So next we move on to the next thing. This is when x2 also has a value and x1 also has a value, so this is the optimal point out here. And next we move on to the third iteration, where we try x5 in a basic variable, and we do the same xb math and z math and the optimality test. And optimality test again makes z4 variable 0, x4 variable 0. So what this indicates is that even this is a basic optimal feasible solution. Again, when you replace this variable in the basic matrix, you're going to get the same equation and you're going to repeat the same solution. So what this means is there are multiple optimal solutions in this case, because because the iso contours, when they move, when the iso contours they move, this is the C position, the previous iteration 2, the position of iteration 2, and this is the iteration 3. Both lie on the same line. See, the iso contour when moved lie on the same line. So you have multiple optimal solutions. That's it.